In this video, we're going to be continuing our discussion of transfer functions, sinusoidal transfer functions, and applying these tools to understand uh, what's called the frequency response of a system. And we might start to talk about filters as well. Um, so I'll go ahead and put up a circuit example here where I've got some voltage source uh, with going into a resistor, with a capacitor down here, and then connect back to the voltage source with ground underneath. And this is the same circuit that I looked at in a previous video, previous example video. And so for this circuit, we've got a resistance R, capacitance C. The voltage at this node right here is going to equal V in, and the voltage at this node is going to equal, we're going to call it V out. Um, and so we analyzed this circuit. We found equation of motion is going to be RC V out dot plus V out equals V in. And this was again in the previous video. And what we're going to be talking about today is, or in this video, is is to analyze this circuit with a sinusoidal or a harmonic input. So V in is going to equal some sine of omega t. And to do that, to analyze this, we can find the transfer function of this circuit, and that's going to be with initial conditions equal to 0, and that's going to be RC S V out of S plus V out of S. V equals V in of S. So this is that we take the Laplace of both sides of the equation. And then we can factor out V out of S equals RCS plus 1. V out of S times V in of S. And now our transfer function, G of S, is going to equal V out of S over V in of S. And that's going to equal 1 over RCS plus 1. So if we're looking at this, first of all, we know that the pole, we're going to have one pole, so so we'll find the value of S that makes the denominator equal to 0. So RCS plus 1 equals 0. That means that S equals negative 1 over RC. And given that R and C are parameters of real resistors and real capacitors, they're positive. So this pole is negative. It's on the left half plane. So that means that this transfer function, the system, is stable. And at this point, we can plug in G of S equals J omega. We can plug in J omega wherever we see S in the transfer function, and that's going to give us our sinusoidal transfer function, where we have 1 over RC J omega plus 1. This transfer function, we can view it as a complex number divided by a complex number. So 1 is in the numerator is 1 plus 0 times j, and in the denominator now I'll rewrite it as 1, which is our real value, plus RC omega j. And if we rewrite this in magnitude phase form, we have some magnitude of G of S times E to the J times the phase of G of S, or G of J omega, sorry. S equals J omega. And the magnitude of G of S, bit of a shortcut when you're dividing complex numbers, is given in this is discussed in chapter 14. That equals the magnitude of the numerator divided by the magnitude of the denominator. In this case, the magnitude of our numerator is just 1. And the magnitude of the denominator we can find by the Pythagorean theorem. So it's going to be the square root of 1 is our real component squared plus RC omega squared. And then the phase of g of j omega is going to equal the phase of the numerator minus the phase of the denominator. And the phase of the numerator, so I'll go ahead and draw this vector here. So the numerator is just, here, I'll go ahead and draw it with a color so we can see here. Numerator is just the real number 1 right there. So the phase is 0. There is no angle, there's no difference between that vector and the real axis. So the phase of the numerator is 0. And the phase of the denominator is a tan 2 of the imaginary part, RC omega, and the real part, which is 1. So now that we have this sinusoidal transfer function written in magnitude phase form, this becomes really convenient for us because the magnitude of g of j omega is equal to the magnitude of the steady state response of V out. And similarly, the phase of g of j omega is equal to the phase offset of that steady state response as well. So we've written this before that the steady state is going to equal some b times sine of omega t, we said plus theta plus phi. And so this b is g, the magnitude of g of j omega. And this phi is the phase of g of j omega. Theta would be known from the input of the system, and omega is now a variable where at any given frequency, at any given input frequency, we can calculate the value of b and the value of phi to predict what the magnitude and what the phase offset of that response is going to be. And so in this particular example, if we plug in, if we'll say that R equals 1000 ohms, which is 1 kiloohm, and C is equal to a millifarad, 1 millifarad, we end up with responses that look like the following. So the magnitude which is g of j, the magnitude of g of j omega, is a plot that looks like this, where it's on a log scale. So we've got 0.1 radians per second, 1, 10, 100, 0.1, and 1. It's going to look about like this. It's going to go straight, and then it's going to start curving down as it gets down to 100. And the phase is going to look like this. And these plots just come from plugging omega into the magnitude of g of j omega and the phase. So again, we've got a log scale for frequency. 0.1, 1, 10, 100. And we'll do a linear thing here with between 0 and negative 90 down here, degrees, negative 45 degrees. So this is the phase. And this is going to start up at 0, and then it's going to swoop down to negative 90. And it's going to hit negative 45 right at 1. And so with these plots and with these functions that we have, magnitude and phase of g of j omega, we can predict at any given frequency what the magnitude and phase offset of the steady state response is going to be. And we'll go ahead and end that video right there.